Okay, a warning everyone, this is going to be recorded, so be on your best behavior. So it's a great pleasure to introduce Stephan. Stephan's going to talk about groups acting on trees from finite combinatorial data. Over to you, Stephan. Thank you.
All right, thank you very much, Stephen. So I think all the Zoom participants can now hear me and see my presentation. Colin, can you wave your hand if that's correct? Yes, excellent. All right, so we can get started. Okay, first of all, thank you very much for the warm welcome in Perth here. I've had a good time so far, and from what I hear, it's only going to get better next week, so I look forward to that. And thanks for the opportunity to give this presentation here. So yes, groups acting on trees from finite combinatorial data, because that's what people here do, right? So let me first give you the 2-minute summary of what I'm going to speak about. So I study groups acting on trees, and when I say trees, I mean typically infinite trees like these. So if you see them fading out towards the boundary there, you have to imagine the regular pattern continuing up to infinity. And so I study these groups from the point of view of topological groups. So the automorphism group of one of these infinite trees comes with a topology, and it works such that two elements are close to each other if they agree on a large part of the tree. So something is close to the trivial automorphism if it fixes a lot. All right. So the way I study these is it turns out that global properties of these groups, like their normal subgroup structure or properties of certain globally defined subgroups, are deeply connected to what these groups do locally on the tree. So for example, if I fix a vertex like the middle green vertex in the right-hand side tree here, then that stabilizer induces a permutation group on the neighbors of that vertex, and properties of this permutation group sometimes say something about the global structure of the group. Okay, so that's the theme from local to global. And I want to introduce two classes of groups acting on such trees for which this connection is particularly strong, and then focus on what exactly this combinatorial data is that classifies them. If you ever want to draw trees like that, there's a tool on our website where you can do that. All right, so before I get into the actual constructions, let me tell you what sort of statement we're aiming for. And this is going to be a bit technical, but the philosophy is really quite simple. So if you're not usually dealing with topological groups, just focus on that. I'm going to take a totally disconnected locally compact group. So the standard example is one of the automorphism groups of one of these trees in the topology I described before. And I'm going to make two definitions. The first one, this H infinity thing, it collects all the closed co-compact normal subgroups. So think of that as a big normal subgroup. If it's co-compact, that means the quotient is compact. So it's a big normal subgroup. And then there's what's called the quasi-center, QZ of H, and it collects all the elements whose centralizer is open, and that applies to discrete normal subgroups. So I think of discrete normal subgroups as small and co-compact ones as big. All right, and I collect them in these two subgroups of H. And now here's a statement which takes groups acting on trees or graphs more generally, like the ones we've seen before, and makes local assumptions, and then says something about local global properties involving these subgroups. So if you have a subgroup which is locally semi-primitive, so the action that vertex stabilizers induce on neighbors is semi-primitive, and it's non-discrete, which in this topology just means that vertex stabilizers are infinite rather than finite, then you have the following. This H infinity thing, it's still co-compact, it's still a big normal subgroup, and the quasi-center is still discrete, so it's still a small normal subgroup. And every other normal subgroup either sits above H infinity or below the quasi-center. So this statement number 3 is really saying that all normal subgroups, well, closed ones, are either big or small. And so what happens with the subquotient in the middle? You would hope that there are no normal subgroups there, and it's almost It's almost as good as that. This subquotient in the middle has minimal normal subgroups and they're topological simple. And in most cases, it's actually a direct product of these simple subgroups. So that's, you can understand the thing in the middle and you have the normal subgroups above and below. But really focus on the philosophy of this statement. You have this local assumption of being locally semi-primitive, and then you have this global normal subgroup structure. And this was first proved by Berger-Moses about 20 years ago in the case where the local action was quasi-primitive. But then at some point during my PhD, you guys started talking about semi-primitivity a lot, and I had a look at that, and it actually works for that as well. So that's that. Here's another statement of that sort. Again, if you have a non-discrete group, but this time acting on a regular tree, TD, regularity D, then again, if it's locally something, if it's locally transitivity, then this quasi-center contains no edge inversion. Okay, and then this hierarchy continues. If it's semi-primitive, then it also contains no non-trivial element that fixes an arc. If it's quasi-primitive, it can't even contain anything that fixes a vertex. And if it's K-transitive, then, well, it can't have translations of length up to K. So again, the philosophy is I have a local assumption and I have a global outcome. All right, so that's from local to global structure. Now, since we're talking about these local assumptions so much, let's also know this theorem is essentially sharp. There's another statement which says, well, for example, if the group is intransitive locally, then it can have an inversion in the quasi-center and so on. But since we're talking about these local assumptions so much, it would be good to have some examples at hand which have all of these properties, right? Give me a group that is locally quasi-primitive. And that's really the motivation for this first construction. And I've talked about this a few times before, so some of you may have already seen this. Generalized universal groups, again, it's after Berger-Moses from 20 years ago, but slightly generalized. So let me tell you how this definition works, or how this construction works. I start with the regular tree TD on the top left-hand side there. And I color it in a regular fashion in such a way that every vertex sees exactly all the colors around it, red, green, blue in this case. Okay? And then I have an automorphism of this tree G, and it takes X somewhere else. And it can do anything. It doesn't have to preserve colors. You know, X can go anywhere in the tree, any automorphism. But now I want to make sense of what I mean by a K local action of that automorphism around that vertex X. What does it do on the ball of radius K around X? So to do that formally, I define another tree in the bottom left-hand corner, a finite one, which happens to be isomorphic to a ball of radius K in the big tree. Okay, I call that BDK. And let's call it center B. So then there is a unique color preserving homomorphism of graphs, which sends B to X. So literally just takes that tree, drags it upstairs and matches up all the colors. And then on the other side, I can take the ball of radius K around GX and I get a unique color preserving map to this finite ball. Okay, and if I go around, I get what I call the K local action of the automorphism G of X. It's some automorphism of this finite tree BDK. Again, not necessarily color preserving. Okay, and with that, I can define an interesting class of groups. Okay, so for any subgroup of this finite tree BDK, I define a group UK of F, and it consists of all automorphisms such that whatever vertex I look at, the K local action is always in this group F. Okay, so for example, if F was the whole thing, the whole group aut BDK, then UK of F would just be the whole automorphism group of the tree. If F is trivial, then I would get the group of color preserving automorphisms of the tree. And in between, I get something else. Okay, that's the definition. Here are some properties and questions about it. So the definition again, something that's easy to see, for example, is that whatever F I choose, the group is going to be a closed subgroup in the topology I described earlier. It's also going to be vertex-transitive, right? Because you can always take two vertices, send one to the other, and then make it so that the colors are preserved. And then all K local actions will be trivial. So that's always an element of UKF or NEF. And it's also compactly generated, which is important to us coming from the topological group's point of view. It's really a topological way of saying that it's finitely generated. And if you deal with finitely generated groups, or if you deal with abstract groups, well then, if they're not finitely generated, you can't really do much. So we typically want them to be compactly generated. But the question is, well, what class of groups do I really get? If I let F go through all the possible subgroups of odd BDK, what is this collection of UKs of F? So in other words, can I classify the UKs of Fs? I mean, it looks like they should be in one-to-one correspondence with the F, right? Because, you know, that's how they're defined. But that doesn't quite work out to be the case. So it could happen that while I'm allowing these K local actions to be anything in F, it could be that they are actually less than F because of compatibility issues. So another way to phrase this question is, if I take UK of F, but then fix a vertex in the tree, what action do I induce on the K ball around that vertex? Is that really all of F, or is it less? And it, like I said, it can sometimes be less than F. So I want to understand this condition better when it is exactly equal to F. And I call that a compatibility condition. And there's a reason for that, as we shall see in a minute. So I say that F satisfies condition C if this is the case. The local action, sorry, the action that vertex stabilizers in UKF induce are always exactly F rather than less. So to understand this, well, obviously we have to deal with the automorphism group of these finite trees, right? And there are different ways to look at that. You could just say, okay, it's a Reith product of S3 acting on 3 copies of S2. That's how maybe you would usually do it, but that's not the best way to do it for this condition. The way I want to do it here is I say, I really think of an automorphism of this ball of radius K as what it does on the K-1 ball around the center, and then the K-1 balls around all the neighbors of the center. So here, sigma K-1 GB, K-1 around the center, and then here I have the tuple of things acting on the neighbors of the center. And you see these K-1 balls, as K gets large, will overlap quite a bit. So it's not an efficient description of this automorphism group, but it is what I need to make this condition look more or less, well, at least a little bit pleasant. Okay. Feel free to interrupt me at any point, of course, if you have any questions. Although that won't apply to Zoom participants because I can't monitor the chat at the same time. So we'll look at that at the end. Okay, anyway, that's how I describe these automorphisms. And then the way this condition works out is the following. For every direction that I could walk in from the center, so I in 1, 2, 3 up to D, and for every element of the group written in this way I've described above, there is another element of the group which has the property that its ith coordinate in the tuple here is swapped out with the local action around the center. So you see alpha and alpha I have swapped position. And all the other coordinates, I don't care what happens there, as long as it's still an element of F. Okay, but this is the condition. For every exists something. And you can think about why that makes sense. If you want this group to act like F, sorry, if you want UK of F to act like F on K balls, what do you have to do? Well, you have to take an element of F, let it act on a 2 ball, and then somehow extend that to an automorphism of the whole tree such that the K actions around every other vertex are also in F. In particular, the K actions around all the neighbors should still be in F. And if you look at the first neighbor, for example, from its perspective, it looks like what used to be the local action on the outside in that direction is now at the inside. And what used to be at the inside is now at the outside. That's where the swapping alpha and alpha I comes from. So I'm after subgroups of odd BDK which have this property C. And it's obviously, well, we're in a finite setting and its description looks all right. So we can try to figure that out computationally. And that's what I've done, what I've spent some time on last year together with a student in Newcastle. We've developed a gap package which does exactly that. Well, first of all, find subgroups with this condition and then, analyze them and connect them to the theory of the paper, really. So it's all about these finite trees or BDK. And to make that, to turn that into something that's manageable by a computer, first of all, I replace the coloring with the labeling. Instead of red, green, blue, I have 1, 2, 3. And GAP is going to think about subgroups of the automorphism group of these trees as permutations on the leaves. So I also label the leaves of 1 up to however many there are. Okay. And I sort of do it in a lexicographic fashion with respect to the labeling here, but it doesn't really matter as long as you make a consistent choice. So let me, actually I wanted to show you how that works. So you can still see the permutation here. Now I have a terminal, we can see that too, yeah. So I'm in GAP now and I can load this package. It's called Ugali, by the way, Yeah, I've recently switched from a Swiss keyboard layout to a US keyboard layout, and that means brackets are multiplication signs. So we're up to version 2 now. And the sort of thing you can do is, okay, well, first of all, we can get a hold of this automorphism group of one of these trees. Let's call that G, say. Okay, and you can really see it's, so you have a permutation 1, 2, you can swap those two leaves, 3, 4, 5, 6, and so on. And let's say we take a random element of this group. Here it is. It's a permutation on the 6 leaves, but I would like to write it in this fashion here. I would like to decompose it into all its, 1 local actions in this case. K minus 1 is 1. So I could ask, what is the 1 local action of this element A, which acts on a 3-2 ball at the center? And it's going to be some permutation of the letters numbers 1 up to 3. And then I can look at all the neighbors, 1, 2, and 3, and I get all these local actions. So that would be decomposing the element into that form, right? And then I can ask, well, is there a compatible element acting on this ball inside this group G compatible with A in direction 3, for example? Okay, so the I over here would be 3. And something has gone wrong. Okay, this should just be a number, not a list. Okay, and yes, there is a compatible element, great. And we can verify that, maybe let's call that something, oops. Let's call it B, and then we can verify that its local action at, say, in direction 3 is 1, 3, 2, which used to be the local action of A at the center. Okay, and similarly, at the center, I now have what used to be the action in direction 3, all right? And everywhere else, I don't really care. Something happens as long as it's still in the same group. Okay, so from this perspective, it's an educational tool so far, let's say. But then I want to I don't know, get a hand on lists of groups that satisfy this condition C, right? So what could I do? For example, in this tree of radius 2, I could say, okay, I want something which acts like the alternating group on 3 elements around the center, okay? And then what groups acting on the 2 ball are there which do that and satisfy condition C? So then first of all, I have to turn this into a local action. It's just a category introduced by this package, which makes the group remember the degree and the radius. So 3 and 1 in this case. Let's call that A3. And then similarly, I could do this for the symmetric group. And so now I can ask, well, what are all the conjugacy class representatives of compatible subgroups with this specific projection, let's say A3, acting on a ball of radius 2 of the same degree as A3. Conjugacy class. Yeah, I've also recently renamed things. So there's only one group, okay, but then for S3 there are 5 subgroups, or conjugacy classes rather, which have this condition C. And if you're familiar with Weiss's conjecture, for example, which states that there are only finitely many conjugacy classes of locally primitive vertex-transitive discrete groups, you can find some examples here. You can now do something like, you can filter this last list by which of these groups also satisfy what I call condition, or satisfies condition D for discreteness. It's another, combinatorial condition on these groups, which tells me whether the thing is going to be discrete or not. And then there are only 2 groups. And the one coming from A3 will actually also be discrete. And if you go to the next radius, if you go to radius 3, you will find 2 more. So then you have 5 discrete groups. And you will only ever get these 5 out of the 7 that there are by Tits work, if you're familiar with that, because the other 2 don't fit into this universal group framework. Yeah, but if you like, if you could do this for other local actions and then look at it as a way to produce lower bounds for Weiss's conjecture, if you like. Yeah, Michael? I'm going to tell you in a minute which ones you don't get. All right. So back to the presentation. How am I going for time? Looks all right. So, okay. To finish the discussion of these universal groups and lead into the next construction, I'm going to talk about independence properties briefly. So Chris Banks, Murray Elder, and George Willis a couple of years ago defined the PK closure of a group acting on a regular tree, or any tree really. It used to be just called the K closure, but then we heard that K closure already has a meaning for permutation groups and it's different. So we renamed it to PK closure. And it does the following. It says, okay, in the P closure, I want to collect all the automorphisms which on balls of radius K act like an element from H. Okay. For every vertex, there's an element of H such that G and H agree on that ball. So, yeah. So, yeah, all the elements which on K balls act like an element from H. And that could be a different element from H on every K ball. And then I say that something is PK closed if performing this operation doesn't do anything to the group. And you can look at that as a kind of independence property, because it says that if you do something on a K ball here, that doesn't have any implications on what can happen on the K ball here, because they could be completely different elements of H. That's why these are called independence properties. Okay, and these PK closures are useful because they approximate the original group H, and that you can already see that that makes sense intuitively. If you act like H on larger and larger balls, well, you're going to get closer to H somehow, right? So to make this precise, you have this descending sequence of K closures, and if you intersect all of them, you get precisely the closure of H. So if H was closed to begin with, you would get H back as this intersection. And now I can tell you what class exactly I get with these finite permutation groups that satisfy condition C. If I restrict myself to locally transitive ones, so transitive on around the center, and condition C, I get precisely locally transitive groups acting on the tree. which contain an inversion of order 2, an edge inversion of order 2. Could have any even order, but there has to be at least one of order 2, and satisfy one of these independence properties. And now, Michael, you can see which of the 7 groups of TUT you don't get. You don't get those which don't have inversions of order 2. There are 2 which only have inversions of order 4 or more. So yeah, you get this nice one-to-one correspondence between this class of groups acting on trees and these, permutation groups with this specific particular condition C. Sorry, yes. Oh, yes, yes. I mean, PK close. I should have written that. Yes. Yeah, and that's really what makes the whole thing work, right? If I didn't have this independence property, then, there's no hope of getting the whole group into this finite information F here. That's what makes it work. Yeah. All right. So now we have the second construction, or it's a classification rather. I'm not going to talk so much about the construction. And it just looks at P1 closed groups. So in this sense. Now we've already seen that the U1s of F are going to be of this form. They are U1 closed. So this is the Venn diagram to relate this construction to the previous ones. You have the UKs and the P1 closed groups, and they intersect in the U1s. And so Colin Reid and Simon Smith have recently come up with a classification of all P1 closed groups, which is quite remarkable and neat, I think. So they classify these groups up to conjugacy in an object that they call a local action diagram. And then this comes with an isomorphism, a notion of isomorphism as well. So let me tell you what a local action diagram is, and then get into how exactly this correspondence works. So here we go. A local action diagram is a triple, and it consists, well, foremost, it consists of a connected graph gamma, typically finite. Oh, I should say they do this in quite a large generality for any tree that's not even necessarily locally finite. But to relate it to the previous construction, let's just say we're looking at regular trees. So then I would get a connected graph, and it would be finite. And one caveat here is the definition of graph that we use is almost the same as Serre's definition, where the vertex set and the arc set are just arbitrary sets, and the origin and terminus maps just, associate an origin and a terminus to every arc. But the involution that Serre has, which associates the reverse of to every arc associates a reverse, can have fixed points. So an arc can be inverse to itself. So that would be, it will only apply to loops because you still have the condition on origin and terminus, but it can happen here. And then what else do I have? So I have these sets XA. Every arc comes with a set associated to it. Okay, think of the arc as being labeled by a set. And for every vertex, I have a permutation group, and it acts on the union of all the sets coming from arcs that come out of that vertex. Okay, so I take all the arcs coming out of that vertex, their sets, take them all together. That's a set XV. And I want a permutation group on that set, which has orbits precisely the XA coming from the arcs. Okay, let's absorb that for a minute. So I have this graph. Every arc has a set, and every vertex has a group, a permutation group, whose orbits are precisely the sets that I see on arcs coming out of that vertex. Okay, that's called a local action diagram. So the way this classification then works is, how do I get a local action diagram from a P1 closed group? Well, the graph is just going to be the quotient graph for the group acting on the tree. So vertices of this graph gamma are going to be orbits in the tree, and then arcs are going to be orbits of arcs. Origin and terminus behave in the way you would think, and so does the reversal map. And these sets, maybe start with the group. So the group at every vertex, since vertices represent orbits in the tree, the local action around those vertices are all permutation isomorphic to each other in the action on the big tree. Right? So now I just take one representative of that class of permutation groups. And then these sets XA, you can think of them, well, they're really just, their cardinality is really just saying, well, in the local action in the big tree, how do these, what orbits of arcs do I get coming out of that vertex? Okay, if I have 3 arcs coming out and they all collapse to one orbit, then I'm going to put a set of size 3 there. Think of it as a color set, if you like. If red and green coming out of a given vertex are in the same orbit, then there's going to be a set of size 2, red and green. Okay, maybe it becomes more clear if I give you some examples. In fact, let's do this. Let's classify vertex-transitive P1 closed groups acting on the tree of degree 3. Okay, so going back to this local action diagram definition, since the action is vertex-transitive, the graph is just going to have one vertex, right? There's one orbit of vertices, but there could be whatever, well, up to at most 3 orbits of arcs. And there's going to be some permutation groups. So let's maybe start with this one vertex, and let's say the local action is the trivial group. Okay, so for example, color preserving automorphisms on the tree. Then I could have, okay, so this group has 3 orbits. So there should at least be 3 arcs coming out of this vertex, and I've drawn them here. And they're labeled by their orbits, well, 1, 2, and 3, the sets, okay? And by the colors, I want to indicate what the reversal map is doing. So the convention here is going to be, an arc is going to be the reversal of the arc of the same color. So if you only see one arc of a given color, it's going to be its own reverse. Okay, so red, green, and blue are all reverse, inverse to itself. And what group acting on the tree is going to produce this local action diagram? It's going to be the universal group of the identity, U1 of the identity, or in other words, all color preserving automorphisms of the tree. It acts vertex transitively, as we've seen before. Any vertex can go anywhere else, and I can preserve colors. And it has 3 orbits of arcs, yeah, red, green, and blue. And each of these orbits contains the inverse of a representative. So if in the universal group, I can take an arc and I can invert it color preservingly. All right, so that's why here the reversal map on the quotient graph is trivial. Everything is its own inverse, because in the action on the big tree, an arc and its inverse are in the same orbit. So I could have drawn a different local action diagram. I could have said, okay, one vertex, trivial local action, but let's say the reversal map is a bit different here. So blue is inverse to itself, but the 2 red loops that you see, they are inverse to each other. They're no longer inverse to themselves, they're inverse to each other. What group does that local action diagram come from? And it is Z free product of C2. So think of Z free product C2 acting on its standard Cayley graph. So you have all these copies of Z, and then you have you know, single edges and another copy of Z, and so on in a free fashion. And the action is, well, again, it's vertex transitive because it's a group acting on its Cayley graph. But now what happens to the arcs and their inverses? All the arcs coming from C2, they are inverse to themselves, because that's what the generator, that's how the generator of C2 acts on that Cayley graph. But on the Z parts, all the arcs going one way are in an orbit, and all the arcs going the other way are in a different orbit. So that's why here these orbits are inverse to each other, if you like, rather than inverse to themselves. That's where this comes from. Okay, and that's, okay, yeah, I should say that's all there is for the trivial local action up to isomorphism. I mean, I could have picked two different loops here to be inverse to each other and then the other one inverse to itself, but it doesn't matter up to isomorphism. So let's move on to the next local action then. It would be, well, any subgroup generated by a transposition of S3. So let's just take 1, 2. That group has two orbits. So there should be two arcs and they're labeled by their orbits, 1, 2, and 3. And here again, I have the choice of having these arcs inverse to themselves or inverse to each other. In the case where they're inverse to themselves, this comes from the universal group for that local action. In fact, universal groups always have this property that every arc is inverse to itself or is in the same orbit. Or I could have done, yeah, I could have said they're inverse to each other. And that situation comes from an end stabilizer of the tree. So think about T3 and now you have some end. If you take the group which fixes that end, it also has local action, just a transposition, right? If you fix one vertex, you have to fix the ray going to that end. So you only can swap the other two vertices there. But the orbits work out, the orbits and the inverses work out differently here. So different local action diagram, different group. And then the other two cases are, well, there's not much to do here. I could take A3 or S3, they're both transitive, so there's only one orbit, one arc labeled by that orbit, and they come from universal groups. And again, if you like, and this is not packaged yet, but I've written a little thing in GAP which outputs these local action diagrams. Well, not nice pictures as in the presentation, but at least the data behind them. So the argument here will be degree of the tree, and it will output all vertex-transitive P1 closed groups acting on that regular tree, given by their local action diagrams. So there's a group here, as you can see, trivial group, transposition, alternating group, the whole group. Then there's the set of arcs given by how they're labeled, and the reversal map given as an involution on the set of arcs. So trivial map means everything is inverse to itself, or you know, arc number 2 and arc number 3 are inverse to each other, and one is inverse to itself, and so on. And one obvious question is, could you try to count these, for example? Can you try to count these local action diagrams for, well, in this case, for example, for a given D? It somehow depends on the number of, It depends on the number of conjugacy classes of subgroups of the symmetric group, but also how many different involutions there are on their orbits. And this can get arbitrarily complicated. You could, I mean, these are just the vertex-transitive ones. If you have something that's not vertex-transitive, the quotient graph is going to have more vertices, and then each of those vertices is going to have some local action, and that's going to have orbits, which determines how many arcs come out of that vertex, and so on. Yeah, and so what I haven't said is, how do you go from the local action diagram to the group? And I will admit that I'm not completely familiar with that, but it is, it is the largest part of the work that Colin and Simon have done in this paper. So going from the local action diagram to a group and showing that it's one-to-one. Yeah, so we're at 4:45 now, roughly. So maybe that's a good point to stop. So in summary, we have I study groups acting on infinite trees. We have two particular classes here where there's a strong connection between local properties of the group and global properties of the group. In fact, so strong that there is a classification in terms of finite combinatorial data, which can look like this. And that makes these classes of groups, well, open to computational methods. And that's what I'm trying to do at the moment. And there's many open questions around that. And well, I'd be happy to talk about some of them during my stay here. And yeah, maybe let's leave it at that.
Thank you very much, Stephan. So are there any questions for Stephan? Michael.
For your PK closed groups that have that chain H1, that they all contain H bar.
Yes.
Do you have examples of H where that is the chain, or some value of K for which
Maybe repeat the question.
Yeah. So the question is, for any group acting on the regular tree, I get this chain of PK closures. Are there examples where the chain is actually properly decreasing, or does it always terminate somewhere? And yes, there are examples where it's properly decreasing, but it won't be for one of these groups UKF. For UKF, it'll stop at K, and afterwards it'll be constant. So what you can do is, you can, if you choose F1, 2, 3, up to K and so on carefully, and take the intersection of U1, F1 with U2, F2, U3, F3, and so on, if you do that carefully, you can make it so that it's actually properly decreasing. Yeah. But you still get some non-discrete, you can still get some non-discrete group out of it at the end, at the intersection. Yeah. Good question. Anything else here? Oh, I might look at the chat. Now the chat looks empty. Good. Everyone's satisfied.
Well, let me ask one more question. So, so with your local action diagrams, well, with your gap package, you can investigate local action diagrams.
Oh yeah, not really. At the moment.
Yes. Okay. So, sorry.
So you were asking about the gap package for local action diagrams. It's not quite a package yet. It really is just this one command which lists them. Yeah. So there's more work to be done here. Yeah.
Right. Okay.
The other package is more substantial, and that's on GitHub and so on. But this one isn't. Yeah.
Right. Right. Okay. So, what are some of the open questions? What are some of the open questions?
What are some of the open questions? Well, I'm going to talk about one of them next Tuesday. But there's many. So I mentioned an obvious one here is counting these things for different parameters, right? But then there's also, so there are many statements in Collin and Simon's paper of the type, if the local action diagram has such and such property, then the associated group has such and such property. And it's often a translation from combinatorial property of the diagram to topological property of the group. And there will be questions of that sort, for example. How can you, okay, take a given topological property of the groups. How can you phrase that in terms of the local action diagram? That's a type of question. Yeah. Yeah. And there's a few more which require a bit more detail, I imagine, than what I can explain here. But yeah, next week.
Is that for a combinatorial characterization into version, or is that?
Okay, you're pointing at my last slide that I have omitted. So the strategy for my Dakra project is to indeed take these two constructions that we've seen of UK universal groups and P1 closed groups and combine it into a classification of all vertex-transitive groups acting on the tree. So the way I would like that to go is I start with the 0 closed groups. At the top, there's only one, the whole group. Then I take all the 1 closed groups, which are classified by Colin and Simon. Then I would like to classify all the 2 closed groups, 3 closed groups, and so on. And the UKs are going to be examples at each respective level. And then if I take an array or an end of this structure tree, if you like, it's going to represent a closed vertex transitive group acting on the tree by intersecting everything that appears along that ray. So yeah, we have a horizontal classification at level 1, and we have examples at each other level. So now can we combine the two somehow to get the whole picture?
Is there already one direction, like a reduction that sort of fits a little bit? You don't know how the previous are. So going from 2 to 1 is there a natural reduction?
Can you rephrase that? A reduction going from
P2 closure to P1 closure, but be sorting out how big pre-images are.
There's not much in that direction yet, I would say, except that, well, I know some examples at level 2, but I don't know all of them. And so the trouble is, with these local action diagrams for P1 closed groups, everything is nice and independent of each other. I just take a graph, I can pick whatever group I want at every vertex, and then I just have to, well, I'm restricted by their orbits as to what arcs I can choose. But if I were to do something like that for P2 and so on, because 2 or in more generality, k-balls intersect in the tree, there's going to be some compatibility issue in the local action diagram. So that's what I want to figure out in the next 3 years. Yeah. OT3 subscript omega is the stabilizer of an end of the tree. Any end, they all conjugate to each other. Yeah. Yeah, it's a funny subgroup. If you fix an end and also fix a vertex, then, well, you have to fix the whole ray and you have local action transposition, but the orbits are funny. Yeah.
Alice.
You have a lighter question.